Well, I think we'll go ahead and get started. So I want to say welcome to the folks joining us online, and we've got a little audience here in the room today for our next Sustainable Energy Seminar. If this is your first time joining us online, my name is Scott Williams. I'm the Research and Education Coordinator at the Wisconsin Energy Institute. And the Sustainable Energy Seminar is something that we do every other Monday, 3:30, to highlight the many different ways that different disciplines here on campus understand energy challenges and develop solutions. So we're hearing from folks from engineering and science to social sciences and humanities to explore the many ways that different disciplines understand energy challenges and develop solutions. For those who are joining online, you can post questions in the Q&A or type in the chat. I'll be monitoring that as we go along. We do have captioning available if you want to click on the show caption button. And yeah, that option is available if you do need it. I think that's all the announcements for now. I'll just go in my notes here and introduce today's speaker. Juliana Pacheco Duarte is Assistant Professor of Engineering Physics here at UW-Madison. And her primary research focus is in the safety and thermal hydraulics analysis of advanced nuclear reactors with a focus on light water cooled reactors. And today she'll be talking about some research related to our current fleet of nuclear light water reactors and the possibilities of increasing the power output, but also the safety issues involved. So welcome.
Okay. Thank you for the introduction, and thank you for the brave students that is here today, despite the weather. So I will break this presentation to give everyone the needed background to understand some of our current research on boiling water reactors. But I will talk a little bit about what is the current fleet of nuclear reactors that we have in the United States today. The definitions of power operates and what has been done up to today, and the motivations. Why do you want to look into that for now in the near future? And then I'm going to be talking a little bit more in depth about my research, my current research on boiling water reactor instabilities. Some of you might have seen these kind of plots. The nuclear energy today in the United States corresponds to about 20% of the total electrical energy produced in the country. And this 20% is produced by 92 nuclear power reactors that are currently in operation. We do have 2 reactors under construction, and that's it today. These 92 power plants, they have the capacity to produce 94 gigawatts of electricity, as you can show here in the left side, if you're looking to zoom of the slides. And these 20% of energy production has been kind of stable over the last decade. So this is a stable number that nuclear energy has been contributed to clean energy in the country. These 92 nuclear reactors, they are of 2 main kinds. They are all light water reactors. We use light water, we use like H2O as a coolant and moderator of these reactors, but we have mainly 2 kinds, boiling water reactors and pressurized water reactors. So I will be talking a little bit about these reactors. Some of you might be familiar, some of you, this information might be new, but the main difference between boiling water reactors and pressurized water reactors, it is the primary loop where you have the reactor vessel and you have the nuclear fission occurring in the core, producing energy, and this energy is transferred to the coolant, which is water in both of the reactors. The boiling water reactors, they operated with at lower pressure. I put it here, about 7 to 8 megapascal, which is 70 to 80 atmospheres approximately of pressure. Then the pressurized water reactors that operates in the primary loop at 15, 16 megapascal. The boiling water reactors that you can see in this cartoon here, the water inside the reactor vessel boils, becomes vapor, and the vapor goes direct to the turbine, moving the turbine that is connected to the generator and produces electricity. So the same water that flows to the reactor core, it is the water that flows to the turbine and then to the condenser at relatively lower pressures than compared to a pressurized water reactor. The pressurized water reactor, the yellow and red primary loop here, it is the, we call that the primary loop, and contains water at liquid phase. So we're gonna have almost no boiling occur during normal operation. So this water is very high pressure, so we don't have the water boiling, and we're gonna have a pressurizer to keep the pressure high, and we're gonna have a steam generator. At the steam generator, the heat transfer from the primary loop to a secondary loop. And then the water that is flowing in the secondary loop passes through the steam generator, boils, and then this vapor goes to the turbine, moves the turbine that's connected to the generator. So this part is the same, but now the primary and the secondary water, they don't mix to each other. They are completely separate. So these reactors, this is the general idea of these two reactors, but they do also have different generations. They also have different designs. Within the boiling water reactors, the main difference here, we're going to be regarding the containment. So this building that surrounds the reactor, in this case here, the containment, make sure you have my pointer here. We are also going to be closer to your reactor vessel here outside. They're going to vary from one design generation to another. So here are examples of the General Electric designs. The Mark I, Mark II, and the Mark III containment. The containment are designed with the same purpose in all of these three kinds. And the purpose is to condensate the steam and contain the fission products release in the case you have a loss of coolant access. In the case you break a pipe or we have breaking the structure of a primary system, you're going to have release of reactive material and release of high temperature vapor. And these containments have the function to condensate them and to contain these fission products that are, so they are not released to the atmosphere beyond the reactor beyond the reactor building. So the very high level descriptions, the Mark III consists of only a primary containment and a dry well that helps to contain these fissions, while the Mark II and Mark II designs, they contain this dry well and also wet well, which is the suppressed pool that you can see in the drawing for Mark I and Mark II below the reactor vessel. In terms of the pressurized water reactors, one of the main differences we're going to see between different pressurized water reactors, it is how many loops they have into that primary system. So these pictures here are Westinghouse primary systems for 2, 3, and 4 loops. What do I mean for loops? At the center of each of the drawings, you have the reactor vessel, where the fission occurs and the energy is produced. But for each loop, you're going to have one pump and one steam generator. And the steam generator is responsible to transfer the heat produced by fission to the water loop in the secondary side that are going to move your turbine. For all of these 3 different designs, you only have one pressurizer in one of the legs of this loop, because you only need one of them to maintain the pressure at the operation pressure. I didn't highlight in the previous slide, but if you see at the top of the slide there, volume water reactors power, also very strong. Who is the vendor and which generation we are talking about? But we're going to be producing 2.9 to 4 gigawatts of thermal power, which is the power produced in the reactor core. And this power, once it's transformed to electricity, because we're using Rankine cycle, we're going to be reduced by about 35% of this thermal power because of the efficiency of your thermodynamic loop. But we're talking about reservoir reactors, the size of the reactor, we also impact the power. So for two loop BWRs, you're talking about 16 to 18 megawatts of electricity, of thermal energy, sorry. If you talk about three loop nuclear power plants, you talk about 26 to 29 megawatts thermal energy. And if you're talking about 4 loops, you're talking about higher power levels. We talk about 34 to 38, and these are rough numbers of these reactors. So what are power uprates? Power uprates are ways that you can increase the power that the reactor was originally licensed in order to increase our cost effectiveness. So you wanted to produce more power and decrease your costs. So you have to go to this regulatory process that is going to allow you to increase your power by a percentage of the original power that the reactor was licensed for. There are today 3 categories of power uprates. The first one that we call measurement uncertainty recapture. It is a small uprate that about up to 2% of the original license power that accounts for the use of more precise measurement techniques. So if you license your reactor for 1,000 megawatts thermal, and you want to increase 2% that because we have now more precise measurements, more precise instrumentation, a way to measure the power and the flow rate in your core, that allows you to decrease that uncertainty that you had before and submit a licensee for that power rate. And a lot of the reactors have done that since this reactor design several decades ago, and now instrumentation had improved significantly since then. The second category of power uprate, it is up to 7%. And this is called stretch power uprates. These power uprates, they are within the design capacity of the plant. And usually involve changes in the instrumentation set points, but do not involve major plant modifications. So we're still going to use basically the same plant that we have, higher power, but we're going to prove to our regulator, our regulatory body, that this plant can sustain that power. And this is done, of course, going through all the safety analysis and all the transients that you push the boundaries of the safety of this reactor. So this is very plant-specific, a plant-specific problem, and I'm going to talk a little bit more about that later. The third category of power uprates, it is called extended power uprates. And as for today, the maximum power uprate that some of the reactors have been to was 20%. So these uprates do require significant modifications to the major balance of the plant equipment, which can be a pump, it can be a turbine, which like a major equipment that we need in order to have the energy balance in the plant. For that up to 20% of power. So this includes the high pressure turbines, condensate pumps, and motors, main generators, and the transformers of the plants. Several of these power plants have been, and I'm going to show you the numbers about how many has been these power rates. But some reactors, like the larger pressurized water reactors, have not gone yet these power rates. So one of the reasons that I wanted to show that varies in design is to show that are also things about the power density in the reactors that are going to be limitations for how much you can increase the power in this case. The main goal of operating the power reactor is to increase their cost effectiveness by producing more electricity within a nominal cost increase while maintaining the safety of your reactor. So in the United States, and here are the numbers, that have been about 154 power rates approved by the US Nuclear Regulatory Commission in 89 nuclear power plants. So it's 154 in 89 because some power plants have been first to go back measure uncertainty, recapture uncertainty, and then to the stretch power, and then to the extended power rates. So they have been to more than one power rates during their operational life. If you look to the number, these power rates increase the total power by 22 gigawatts of thermal energy. So these represent more 9-10 reactors that we did not build, but we were able to produce the equivalent energy because of this power rates. So it's a significant amount of energy that we can, a significant amount of clean energy that we can add it to the grid without having to build new plants. You can look here, this is per number of power rates, but the total of the measurement certainties are 3,000 approximately. The total of the SPU are 7.8 gigawatts thermal, and the extended power rates 11 gigawatts thermal. So this is the one that can operate your power. Up to today, the maximum was 20% of power compared to the original licensee power. Sure.
Right. So the number of plants that have taken advantage of that is not as much as MU, but even so, the number of plants that have done that have.
Yeah, exactly. So I said we have 92 powers today in operation, now 92 nuclear power plants. So about 30 of them has been through the extended power rate, and that energy was increased about was about 11.6 megawatts, which is equivalent of 3 to 4 nuclear power plants. So it is an expressive amount of energy that we can produce from the current fleet, potentially because of this licensing path that we can take. Before we talk about the motivations that we have today to extend even further our power upgrades, this is a cartoon that shows the safety margins that we have to think about it when we change our reactor power. So we still have to maintain our safety margins during operational, transients, and accident scenarios. So if you start at the top of this cartoon, the safety limit at the top of the cartoon, it is the critical value of an assigned parameter associated with the failure of the system or component. So it is a point that we don't want to get in no circumstance. And you can think about this safety limit as if you have the capacity of your plant or your component of the structure integrity of the reactor and the load that you're putting there. The load can be your maximum temperature, can be your thermal stress, can be several physical parameters. And you're going to have some uncertainty in this capacity and the load that you're putting to the reactor during operation and during access. So the safety limit is there to make sure that we are accounting for the uncertainty and we are far away from the actual capacity of the integrity of the nuclear plant and specific components. Moving to the next level of the cartoon, the acceptance criterion is the quantitative limitation of a parameter or qualitative requirement set up for the results of an access scenario. So here, it is, well, we have our safety limit, a higher there, and this is the number that we can, the number that we have, that we could achieve during the access. So this is the quantitative limitation of each parameter that is put there as our safety margin, as the absolute term of the safety margin. Moving a little bit down in our cartoon, we have the licensing margin, which now it is the difference in physical units. So we're talking about temperature, we're talking about maximum oxidation, we're talking about melting points between the threshold that characterize an acceptance criteria and the result provided by either a best estimate code or a conservative estimate, a conservative calculation. So our best estimate code, as the name says, is the best simulation more close to the reality that we can do. And the conservative approach, as the name says, we're making some assumptions that we're gonna already have some margin included in this. The analytical margin contains an estimate of individual modeling or overall code uncertainties, numeric inadequacy, etc. So these margins here are already talking about our ability to simulate the problem. It's talking about how sure we are that we can model these accidents and all of the phenomena that are going on in the reactor: material science, thermohydraulics, reactor physics, radiation impact in the core. So this talks about our ability to model that. And as we improve our models, these margins also can be reduced because of that. And finally, after we have all the safety margins added, the last one, we still have operational margin that implies states define operation limits and conditions, which includes measurement, accuracy, and controlling range. So this is the margin from the measurement uncertainty power rate. If we improve our measurement, if we improve our measurement of the flow rate, how we measure the power in the reactor, so we have more certain of the state of the reactor during operation, so we can reduce that margin because of that. Make sense? So why we are interested to talk about power operates nowadays? What are our current motivations? I already said there is an economic motivation from the industry because it can produce more power and can sell more energy using the same nuclear power plant. But also the Nuclear Energy Institute has done recently studies that shows that the current state and federal government production credits and tax incentives to reduce the US carbon emissions, it is actually a great incentive for power operates. because that can, as I showed in the numbers that we have today, can provide even more clean energy from nuclear energy without the need to construct nuclear power plants. So that's one of the current motivations. And of course, we have advancements in our field, in our materials, in our knowledge, and these are some examples. The accident fuel materials were materials that was proposed by the industry after Fukushima accidents that are cladding materials and fuel materials that are more tolerant to accidents. What that means? It means that they are more tolerant to oxidation, they have a better thermomechanical behavior at higher pressure, higher temperatures. That could potentially allows us to change the margins that we operate in the reactors currently. Other incentives is the use of higher burn-ups fuel, higher burn-up fuel. Burn-up is a measurement of how much energy in gigawatt days we are producing per ton of uranium. So it is a measurement of the energy that we are producing based on the amount of uranium, metal uranium that we have. So if we're allowed to use this fuel, that you still have a lot of energy once we remove from the reactor core, if allowed just to use that for a longer time or at higher power level, so you're producing more energy with the same mass of uranium, then that's an also incentive. And we are allowed to do that because we are improving our techniques and how we perform and testing the fuel, and we are also improving our fuel with accidental materials and other experiments. Another point, it is also the use of higher enrichment fuels. High enrichment means that we have higher percentage of the fissile uranium isotope mixed in the fuel. So uranium, when you have natural uranium from the ore in the nature, it is about 0.7% of uranium-235. That's the isotope that we actually are using for the fission reactions in the core. The other isotopes, they're going to have a role, of course, but the percentage of the uranium-235, it is what we care at the beginning of our fuel cycle when you put the fresh fuel in the reactor core. So nowadays, we get the uranium with 0.7% of uranium-235, and we increase it to 4 to 5% of this isotope before we put it into the light water reactors that you have in the United States. With the advance of fuel and advance of the industry in general, we are talking now about using a high enriched fuel with 10%. So that's also can allow us to have further power upgrades in our reactor core. With the combination of these technological advancements in our knowledge and advancement in the industry in general, we can enhance the safe performance by decreasing the margins or maintaining the margins at higher power levels. We can improve the economics of the power plants, so decrease the price of nuclear energy. We can increase the fuel efficiency since we are using extracting more energy from the fuel. That's a simplified way to put it. And decrease the waste production. Since we are burning on fuel for a longer time or for higher powers, the same period of time, the total amount of waste at the end of the cycle can also have a significant increase. So these are the current motivations of the industry to pursue this power grid. Now I'm going to switch a little bit to talk about our current research. So this is a research project funded by the US NRC that involves a condition due to power operates boiling water reactors. So this plot here shows the power of operation of the original licensing of the reactor in a boiling water reactor versus the core flow rate, which is usually given by P's in percentage of the original power, but the core flow rate is kilograms per second of coolant, which is our water flowing to the core. So once we increase our power, this example here, it is a reactor that has certain power as original license at 100%, had their power operated by 20%. So you went to the extent power operated. So it was able to increase the power and the flow rate by 120%. Or sorry, the power by 100% and the mass flow rate was here. In this increased core flow rate here, but at 120%. This CBA area in the plot is called Mellon boundary. It's a maximum extended load line limit of some boiling water reactors. A few years ago, there was some applications that wanted to increase the operating flexibility of the operated plants to achieve full core thermal power with a core flow window that is represented by the blue shade area. In this area, it is a condition where you can operate your power at your extended power, but you want to also to decrease your flow rate into the reactor core. So we call that MELA plus or maximum extended load line limit analysis plus. When these scenario came, and there are several of operational, transient, and active scenarios that need to be performed to make sure that we can do that in each particular reactor. So one of the transients, one of the actions that were analyzed is called anticipated transient without scram. And they realized that during this anticipated transient without scram, which is a condition when you have an accident in the reactor, but you're not able to shut down your reactor power. So without scrams means without shutting down the reactor. We could lead these boiling water reactors to conditions that are unstable, that could lead to the damage of the fuel rods, which is what we don't want to happen in an accident. So the ATFs is one of the worst case scenarios, considerations of which frequently motivates NRC to take some regulatory action. So they look to one of the worst case scenarios to see if that condition was safe enough to operate. And when they did that and looked at the unstable conditions that could lead, that raised questions about how we can validate our simulations, how we can make sure you're using the correct models to make a decision regarding this particular condition. And this is where the data that we analyzed in this project, the motivation for the data analyzed in this project came from. This cartoon here in the right side of the slides, if you're not familiar with the word scram, that's the origin of this word. Scram, it means shutting down the reactor. It means safety control rod axeman, because the first reactor, Chicago Pile, in 1942, had a man at the top of the reactor with an axe that in case of need to shut down the reactor, you cut the cord that is holding control rods that you drop into the reactor core and you stop the fission chain. That's an actual story. So if you haven't heard about that, this is always a nice cartoon to show why we call reactor downstream. So the motivation of our research was that there was applications for power uprates at higher power, lower mass flow rates, and during simulations of these conditions, we wanted to understand what are the safety criteria, in this case, what are the instability criteria that you make this reactor unsafe. So NRC commissioned its data from this experimental facility called CATI facility, which is located in Germany, to simulate the volume water reactor rod bundles under ATFs, under anticipate transition downstream. So the facility was chosen because it has this natural circulation loop that it's shown here on the right of the cartoon. Went in the side in the test section here of the volume water test section, we have a full bundle volume water reactor to assemble. So that means that we have 10 by 10 rods. These rods have prototypical power, prototypical heights. They have prototypical grid spacers, like all prototypical geometry with that. The power here, it is not simulated with fission. It is simulated with electrical power. We basically have our rods as a resistance, and we put a current and voltage on them and heat it up, simulate the power. But we can see all the physics in the heat transfer process and in the coolant here. These experiments was done with the intention to characterize the instability conditions of the two-phase flow. Since in the beginning I said volume water reactors, you have water boiling to your reactor vessel and producing vapor. You're going to have two-phase flow, liquid and vapor here, that could lead to oscillations and unstable conditions. These unstable conditions, they can lead to what we call dry out and re-wet cycles, which is the condition that can damage our field because of the high temperatures. And there was also two sets of data that I'm going to briefly talk, but I'm not going to go deep into that. Inside the reactor, there is also a constant feedback between what is happening in the coolant and what is happening with your energy production. The water in the reactor vessel, besides of cooling your few rods and removing the heat and transfer this energy outside your vessel, it also serves as a moderator, which means the water is there to collide with the neutrons, producing the fission product, decreasing its energy, and then the lower energy neutron can produce the next fission. So basically neutrons, they are born in fission with very high kinetic energy, and they need to decrease their energy to cause the next fission. And the water is there also to do that. So if you start boiling the water, you are decreasing your density, so you're being a less effective moderator, which means your power will decrease. If you decrease your power, you're going to condensate the vapor, and you're going to become a more effective moderator to the neutrons, and that's going to make your power increase. So there is this dynamic between the amount of vapor in the reactor core, which you call the void. The void is the fraction of vapor in your core, with the power that we are producing. So one thing very interesting about this data is that this facility was actually for a certain for a set of data was actually varying the power of the bundle to try to simulate also the neutronics and physics of the reactor, besides of the heat transfer and the two-phase problem. So it's a very interesting set of data to look at. Let me show how this data looks like. These oscillations that I'm talking that can occur when you have liquid and vapor, they occur because of the change in the density of the liquid to the vapor that you are producing inside your flow channel that are going to make the velocity of your water to vary along your chain. So if you look to the top left cartoon, if you're looking on Zoom, this one here. At the very bottom, you have your inlet mass flow rate. And each of these waves above represents the local pressure drops that were measured during the experiment. And you can see that it's getting out of phase as we go high into our channel until the exit of your channel, which is more than 3.7 meters long. So we started at the bottom here with a condition that had caused these oscillations, but these oscillations propagate into your two-phase flow channel as we are producing more and more vapor. And because of that, we have a shift between your inlet and your outlet condition. The other cartoon here at the top shows how the experiment was performed. So the green top line here shows the power being increased step by step. The red here shows the flow rate oscillating because it's a natural circulation loop. This is a closed loop. And we're going to have, as you're producing more and more vapor, and of course, the vapor is going to be condensated and also have a constant inlet condition. But this wave is going to propagate in your channel, and you're going to see the effect of the exit at the inlet because of the closed loop. Okay, so as we increase the power, we're going to get at some point that these oscillations are very high in altitude, and they inlet to the exit are completely out of phase, which means 180 degrees out of phase. So this was the work, this is the work of a PhD student that's graduating this May, that shows that we can use these out of phase criteria to show the point of the instability during the experiment. And this point here, where the power was abbreviated for the last time, is when the mass flow rate now is in unstable condition. Although you see a little bit flat here, this is an unstable condition for this kind of oscillation, if that makes sense. There's a lot of information in this slide. But I wanted to, this is what is happening with the flow. If you look what is happening now with the rods has thermocouples inside it. Measure the temperatures, or to what will be the temperature of your fuel rods in the reactor. So if you start having these mass flow oscillations very high and unstable, you can lead to these cycles of dry out and wax and shoot. And now we are looking for the temperature of the rods going to cycles of, you're increasing here 40, 50 Celsius degree, 60 Celsius degree at each cycle of your mass flow. This is the condition that you want to avoid, because eventually you're not going to be able to recover from one cycle, and you're not going to be able to decrease from this high temperature, and your rod can melt. And then you can go to damage on the core, and you can see your accident. So this last cycle here was only decreased because the power of the experiment was decreased. So they were increasing the power until that point, At that point, they don't want to destroy their facility because it's very expensive, so they actually decrease the power and then record all the data and gave it to us to analyze. But what is happening that leads to this temperature increase and decrease? You can see this cartoon here on the right. The phenomena that we call dry out. It is literally the dry out of liquid from the wall of your film. So if this cartoon here show you a few rod, the dry out phenomena, it is where your liquid film, it is dry out here, and then the vapor has a much lower heat transfer coefficient than the two-phase liquid and vapor together. So your temperature of the field just increases a lot. And then when you have your mass flow going up again in the oscillations, we have the re-wet. So the water comes and re-wet the surface. But there are limits. There are temperatures that if you get your temperature very high, you're not going to be able to re-wet, even if your mass flow increases a lot. And you might have heard from about the Leidenfrost temperature. When you're cooking at home and you drop some liquid in your oven or in your pan, the liquid bounces and don't touch the surface. That's because the surface is so hot above these limits that I'm talking here, that even if you try to re-wet, you're not going to be able to. So it's kind of going to be too late for that. So I'm not going to spend much time in this, but it's just for you to see how the mass flow rate in blue here is synced with these temperature oscillations, and how we can analyze what is happening locally to try to define this balance. Sure, the question here was, if ideally I don't want to have any of these oscillations. Yes, ideally. What can happen, and that has happened in some reactors, oscillations can occur, but we should be able to identify them with our measurements and shut down the reactor before a rod gets to this point. Make sense? Okay, thanks. So this is also part of the project, understanding the heat transfer locally to what has happened and what is the moment in this transit that, well, from this point, even if the mass flow is oscillating, we're not going to be able to recover and re-wet the circuit. And this is the point. If the power of the experiments were not decreased here, you'd get high as like 1,000 degrees and you damage a lot. I want to have more time for questions. So we're going to briefly talk. We are not only analyzing the data, we are also using the thermohydraulic computational code developed by NRC that is used for the license purpose, because this code can simulate the entire reactor transit. But we are using this code also to simulate these experiments and compare the results of the code with the data. So this is our current results. I put the name of a PhD student here. That's the student that is working on the simulations and data analysis and developed this plot here, Paul Hurley. The CAT data, it is in these circles and crosses here, or axes here. The axes are for unstable conditions, or the circles are for stable conditions. And the lines that we're seeing, it is our boundary between a stable oscillation and unstable oscillation. So we can have some oscillations here, we do have, but they are not leading to conditions that we consider that are unsafe. So few things here, And PCH is our phase change number, which it tells us the non-dimensional number, so it has no unit, but it tells us the ratio of the power and mass flow. So if your power is high for the same mass flow rate, you're going to go to unstable, which is the beginning of the motivation of this research. If your power is the same for lower mass flow rate, then we can go to an unstable condition. And the other number there, the N sub, is a measurement of the subcoolant of our channel. And subcoolant is how much below the saturated temperature we are at the inlet of your channel. So if your saturated temperature is 300 Celsius and you are at 280, so we have 20 degrees subcoolant. So these are known dimensions, that's what it means. We also compared with some analytical models that were developed back in the days. But we can see here the trace boundary condition is conservative, which means that for these current results, if you use trace, and also for this range, you have a very limited range of experimental data here. For these conditions, if you use trace, you are in the conservative side. We have all of the unstables on this right side of the slides, and also have some stable data in the right side of the slide, right here. So this is good since we are thinking a point of view of licensing the reactor, so this is the good news. We are currently using Parks, which is a software that can be coupled with trace to simulate the dynamics between the reactor physics and the energy production with the thermohydraulics that are happening in the reactor. And these 2023, 2024, we are going to be enter the last year of the project in April. We plan to use scaling analysis to analyze how this data is transferred to full reactor core. So that's kind of gonna gives us a better public available model to predict this kind of phenomenon that helps make the license decisions. So I think we're about time for the questions. These are just a few highlights. I don't have to read them. You can read them. Let me know if there is any question online.
So essentially what you're doing is finding kind of what is the limit in power at different mass flows that can still.
Yes, can she remain safe? That's it, yeah. Correct.
At least this research only applies to boiling water reactors.
This we studied the phenomena, the two-phase flow phenomena, but I'd say the range that we have right now is for boiling water reactors. We do have a literature survey that we did with past experiments, and if you compare everything, then I say it can be applicable to small modular reactors or other reactors that are operating in two-phase flow. Okay. Well, if there is no questions, I'd say the highlights that I want to bring today, it is Well, the power upgrades have been done, but at this moment, I think especially like this and year next year, we have these new motivations to keep searching about these and partner with industry, so we at university can contribute to this power upgrades and how to implement all of these new innovations with accelerated fuels, high burn-ups, high enrichment, to support the industry and produce more nuclear energy used in our current fleet of reactors. So,
I mean, I guess that this sparks. Company, you know, would in testimony, or how would you? I guess I'm not, you know, or is there a common process that you?
that's a good question. I haven't reached this process yet, but the NRC, I not provide, no, I mean, NRC does have open sessions that everybody can provide input, but I think not directly. I mean, there is the regulatory procedure and licensing, which is in the website that has to be followed by the industry. And a lot of things at the point is proprietary. So there is just a part that is public available. So if we're doing that at university, there's a bunch of non-disclosure agreements as we do to access the data. So everything that I presented here today, it's public, but there are details of the data that are proprietary. So
some details you might provide that company that then they submit.
They do their own safety analysis. What we are proposing as a university, it is because we have the freedom to think about different like fuel designs, we can play with that and find, oh, this fuel actually, this configuration, we're gonna give you what we want. And then they do their safety analysis and submit it to NRC. But we can work with more freedom at the university, have your branch to think how to be creative the way to do that.
Any more questions online? Thank you so much for your presentation today.
Okay, thank you.